What specific problem does Emu3 aim to solve within the multimodal model landscape? And how does it differentiate itself from existing methods like Stable Diffusion and LLAVA?
Emu3 aims to address the limitations of existing multimodal models, particularly the reliance on complex diffusion models and compositional approaches that connect language models with vision models, which often fail to achieve competitive performance across tasks. Unlike Stable Diffusion, which utilizes a diffusion process for image generation, Emu3 employs a next token prediction framework that tokenizes images, text, and videos into a discrete space, allowing for joint training on multimodal sequences. This approach enables Emu3 to outperform Stable Diffusion in human evaluations and public benchmarks for text-to-image generation, as well as compete effectively with LLAVA in vision language understanding tasks. Furthermore, Emu3 simplifies model design by eliminating the need for task-specific methods, demonstrating state-of-the-art performance solely through next token prediction, which is a significant departure from the methodologies of both Stable Diffusion and LLAVA. Overall, Emu3's innovative framework positions it as a leading solution in the multimodal model landscape, showcasing its potential for general multimodal intelligence.
Can you explain how the Emu3 method works step by step, detailing the process of tokenizing images, text, and videos, and how the training process is structured?
The Emu3 method operates by first tokenizing images, text, and videos into a discrete space using a vision tokenizer based on SBER-MO-VQGAN, which encodes visual data into discrete tokens. For images, a large-scale dataset is curated, filtered for resolution and aesthetic quality, and then annotated with captions generated by a model fine-tuned on this dataset. Videos undergo a four-stage pre-processing pipeline that includes scene splitting, text detection, optical flow calculation, and aesthetic quality assessment, followed by captioning using a video captioner. The training process is structured in two stages. The first stage focuses on text and image data with a context length of 5,120, while the second stage introduces video data with an extended context length of 131,072, utilizing next token prediction as the primary training objective. This approach allows Emu3 to integrate textual conditional information natively, creating a unified multimodal model that excels in both generation and understanding tasks.
Could you provide a simple illustrative example of how Emu3 predicts the next token, perhaps by walking through a specific instance of video generation?
Emu3 predicts the next token in video generation by utilizing a causal autoregressive approach. For instance, when generating a video, Emu3 first tokenizes a given video clip into discrete vision tokens. If provided with a 2-second video as context, Emu3 analyzes the sequence of tokens and predicts the subsequent frames by determining the most likely next token based on the preceding tokens. This process involves extending the video by generating additional frames, effectively simulating actions or interactions within the video context. The model can generate high-fidelity videos that align with the user's prompt, showcasing its capability to predict future content in a coherent manner.
What are the key theoretical or practical benefits that Emu3 provides over traditional multimodal models, particularly in terms of performance on benchmarks like MSCOCO30K and VBench?
Emu3 offers significant theoretical and practical advantages over traditional multimodal models by utilizing a next token prediction framework, which simplifies model architecture and enhances performance across various tasks. Specifically, Emu3 achieves state-of-the-art results on benchmarks such as MSCOCO30K for text-to-image generation, outperforming established models like Stable Diffusion (SDXL) and demonstrating competitive performance against DALL-E3. In video generation, Emu3 excels on the VBench benchmark, showcasing its ability to generate high-fidelity videos and extend video content by predicting future frames, a capability that traditional diffusion models lack. Furthermore, Emu3's approach eliminates the need for complex compositional methods, allowing for a more streamlined training process and improved scalability during both training and inference. Overall, Emu3's performance on these benchmarks highlights its potential to redefine multimodal model capabilities without relying on task-specific architectures.
How does the validation process for Emu3 demonstrate the effectiveness of the new method, including specific performance metrics or comparisons with established models?
The validation process for Emu3 showcases its effectiveness through comprehensive comparisons against established models across various benchmarks. Specifically, Emu3 outperforms the flagship Stable Diffusion Model (SDXL) in human evaluations and public text-to-image benchmarks such as MSCOCO30K, GenEval, T2I CompBench, and DPG Bench, achieving superior scores in image-text alignment evaluations. In the realm of vision language understanding, Emu3 competes favorably with LLaVA1.6, demonstrating its capabilities without relying on pre-trained models. Additionally, the model's performance is quantitatively assessed using metrics like LPIPS, PSNR, and SSIM, which indicate its high-quality video tokenization and generation. Overall, Emu3's results, including an overall score of 81.6 on the DPG bench, highlight its competitive edge over both autoregressive diffusion methods and state-of-the-art models like DAL-E3, affirming the efficacy of the next token prediction approach in multimodal tasks.
What are the notable limitations of Emu3, especially in comparison to diffusion models or other multimodal architectures, and what steps do the authors propose to address these limitations in future work?
The notable limitations of Emu3, as highlighted in the paper, include its performance in comparison to the most advanced proprietary models like Kling and Gen3 in video generation, where it falls short despite outperforming many open-source models. Additionally, while Emu3 demonstrates competitive results against state-of-the-art diffusion models, it does not achieve the same level of performance as these models in certain contexts, particularly in generating high-resolution images and videos. The authors propose to address these limitations in future work by continuing to refine the next token prediction framework and exploring enhancements in model architecture and training strategies. They also emphasize the importance of open sourcing their techniques to facilitate further research and development, which could lead to improvements in multimodal understanding and generation capabilities. Overall, the authors aim to leverage insights gained from human evaluations and automated metrics to iteratively enhance Emu3's performance.